Just like with any concept in organic chemistry, to demonstrate true understanding, we need to be able to solve practice problems. So that's what we're going to do in this lesson. To make this kind of interesting and fun, I've chosen 4 drug molecules that we can target. The first one is propranolol. This is a beta blocker used to treat high blood pressure and irregular heart rate. It's also sold under the name Inderal. Why don't you take a minute and look at this molecule, pause me, and think about the disconnections that you would propose. And if you can't get very far, at least try to make your first disconnection. Let me show you how I approach this. Cleaving adjacent to a functional group is always a good idea, and we can cleave this bond right next to the nitrogen and add the nitrogen atom in somehow. If we make this disconnection, we'll come up with 2 synthons. So just drawing this at our cleavage point without adding anything in, we'll get these fragments. Now, nitrogen is often a nucleophile, so it makes sense to make this the donor synthon and put a negative charge on nitrogen. Okay, bearing in mind things from our previous lessons, nitrogen can over-alkylate under certain circumstances. And so it's a good idea to use reductive amination or amide formation to arrive at the amine. So if we're thinking about this piece, instead of just making this a synthon, we might think about what we could have on there that would allow for reductive amination to occur or amide formation to occur. And this would be a carbonyl. We require a carbonyl to do both of those reactions. So let's add that on. Now, I'm not sure if this will be an aldehyde or an ester, so I'm just going to place an R group right there. Now, I'm leaving this undefined because I haven't broken up the molecule completely yet, so I'm not really sure what a good commercially available compound is going to be for this. So I'm going to leave my R group on there, but make my next disconnection. Boy, oxygen and oxygen in a 1-2 relationship. That looks like a great epoxide opening reaction. Let's assume this part will be the nucleophile. We don't want to cleave next to the aromatic ring, so if we cleave on this side of the oxygen, we could get an epoxide from this piece. Now I'm going to skip the whole synthon thing here. When I cleave, this obviously looks like it's going to be the molecule 1-naphthol. So we can skip putting a negative charge on this oxygen and go straight to the reagent if we're seeing that easily. Retrosynthesis is just a tool for you to be able to write forward syntheses, and so whatever steps you need to take them, and if you can skip a step, go ahead and do that as well. Remember, when we look at this, we see the positive charge next to an oxygen, and if we imagine the lone pair donating in there, we will be able to visualize our epoxide. Let me draw that now. So I have to admit, in my time in the lab, I've never used an epoxide with an adjacent carbonyl like this. So I needed to go ahead and look this up to see if these types of compounds were even commercially available, and then to determine how they react. So let's go to the web and do a little research. So my main concern in using an epoxide with a carbonyl on it is, how is it going to react? Is the epoxide going to open? Does the carbonyl react? I just don't know much about the reactivity. So we'll go to the Sigma Aldrich structure search page and we'll draw in our epoxide, or as much as we know of the structure that we want. We'll add in our oxygen atoms. We know we want the epoxide and some carbonyl over here. We'll do a substructure search because we really don't know exactly what we want yet. And this will give us some hits. And the most interesting thing to me is the ester is commercially available. So I want to get its common name so I can do this quick info thing and copy that. And then I'm going to go over to Google Scholar so I can figure out, does this thing open up at the epoxide or does it react at the ester first? That's going to be really important for designing our synthesis. In Google Scholar, I'm going to paste our name. I'm going to take out this 2R that has to do with stereochemistry, and I don't really care which enantiomer I get. And I want this in a synthesis, so I added the word synthesis to my search. Now I can scroll down, and I don't want to make it. I want to see it used in a synthesis, and this one looks promising. It also has a PDF available. When we go to this paper, the first table contains the reaction we want above it. And we can see here that entry 6 actually has our ester. And it's produced in really good yield. This opens the epoxide, leaving the ester on the molecule. So we have precedent to open our epoxide and leave our ester in place. Well, now with that information and this precedent, we can go back to our synthesis. Now that we have precedent for phenols or naphthol here, opening up epoxides at this carbon atom and preserving the ester, we can go ahead and write up this reaction. That precedent was using a pretty fancy catalyst, and they were doing an enantioselective process, so that catalyst was making one single chiral compound coming out. We probably don't need to do that for this synthesis because we don't have any requirement to have stereochemistry defined at any of our carbon atoms, but we'll go ahead and just write catalyst. We might be able to find some simpler conditions and make a racemic mixture of this alcohol. So the chiral center I was referring to could be right here, so we could make this enantiopure if we wanted to based on the precedent we found, but we don't have to for this problem. So this is a chiral carbon right here. Okay, our final stage involves condensing this with some sort of an amine. And so here we're going to have the amine form our amide, and then we're going to reduce that amide with LAH. The first compound we need is the amine corresponding to this synthon. Then we're going to reduce it with lithium aluminum hydride. Here I've written LAH. LiAlH4 is the other way to write that. This is just a very common abbreviation. And after using this hydride donor, we're going to need to find a way to neutralize any of it left in solution and work it up. So now we have our synthesis outlined. We have a few things that are kind of missing details here, but we can go to the literature and find good precedent. If we were really going to make these molecules and actually do these syntheses in the lab, we would need to look up conditions and molar equivalents of things used. But here we have quite a good outline for how we would carry this out. So how did our synthesis compare to the way that they actually make propranolol? This is a known drug. They make it a lot. Let's check out their synthesis and compare. We'll learn a few things from this. In commercial production, they actually use a different epoxide, this one containing a chloride leaving group. And in the patent, they claim that they isolate this epoxide from it. So an SN2 reaction occurs with this chloride, or the epoxide opens and closes back down. It's kind of hard to know the mechanism since in the patent, just this compound is reported. Then they open this epoxide by direct treatment with an amine. You might be concerned about overalkylation, but actually the reaction of amines to open epoxides is quite a good reaction. In addition, the isopropyl group on the amine makes the product quite sterically hindered. So all they ended up doing was adding this amine, heating up the mixture, and presumably it opens the epoxide on the least sterically hindered side, and we got propranolol from this. Let's apply what we've learned to the synthesis of another drug, Prilocaine. This is a local anesthetic. Why don't you go ahead and pause me and see if you can propose some disconnections for this molecule. Okay, one thing we should notice, we have a nitrogen with an isopropyl again. And this molecule looks pretty hindered too. So we may just be able to use what we learned in the last example to put on this group as well. Cleaving next to heteroatoms is always a good idea. And so let's go ahead and put two possible disconnections onto this molecule. Here I'm cleaving in the middle of the amide. We'll call this disconnection A, and here I'm cleaving to the left of this nitrogen, and we'll call this B. Let's examine the synthons that would result from each route and see if we can determine a way to go with this. Let's examine the synthons that would result from route A. We have our nitrogen as our donor synthon with the negative charge here, and then we have this carbonyl as an acceptor. Putting a leaving group right here would be a great way to go. And we could do an ester, or even better, we could do something much more reactive that's a more reliable way to form the amide, and that's the acid chloride. Let's look at the synthons from route B. Okay, now our donor is this piece, looking a lot like isopropylamine, and we have this acceptor synthon right here. So when we look at cleaving via route B, we have our donor synthon as our amine, and then we have this cation adjacent to a carbonyl compound. We saw in previous videos that it's pretty straightforward to install a halide next to a carbonyl, and so this is a pretty good synthon too. It's really not obvious to me here which route we should choose, so what I'm going to do is cleave another bond and go back one more step to see if I can make some sense of this. So in this compound, we'll cleave this bond, and let's just assume this is coming from the acid chloride. Okay, so I've shown the acid chloride. If I cleave this bond, I'll need a leaving group here if I'm using the natural nucleophilicity of this amine right here. So it probably makes sense to have two chlorides on the molecule. So we could envision this leaving group maybe as another chloride, and then we have our amine. Let's go back one more step with this one. We'll cleave the amide here, and let's see what we get. So essentially our routes are pretty similar. They both come back to the same compound. So when we're deciding how to make this, we need to think about which side of this molecule is more reactive. That's the acid chloride. These are very activated compounds. So we're going to want to add to this side way before we do an SN2 displacement of this chlorine. Let's see what that gives us for our forward route. Because an acid chloride wants to react at the carbonyl carbon first, we're going to choose this route. Our forward synthesis becomes this. So first we'll get addition of our amine to this side of the molecule, forming this. And now we just need to add in the reagent corresponding to this synthon. This is isopropylamine, which we met in our previous synthesis here. The product of alkylation is very sterically hindered, and so we can form this directly by treating this compound with the amine. This forms this target molecule, which we'll call TM2. So how did our synthesis compare to the one that's actually used? Well, it's really close. They actually use the dibromide here. So they use an acid bromide with a bromine leaving group, probably because that facilitates this step here, with bromine being a better leaving group, and they just need to heat that step up to get it to go. Next, we're going to look at this molecule. This is not loperamide itself, but this is an intermediate along the pathway to synthesize it. Loperamide you might know by the name Imodium. This is an antidiarrheal belonging to the opioid class of drugs. Go ahead and pause me and try to tackle this molecule. Pay careful attention to the pattern of the functional groups within the molecule while you do this. Okay, we might be tempted, like in previous examples, to cleave maybe here first, next to this nitrogen. Well, we don't want to cleave off this group last. That would leave us with an amine, an NH. And amines in the presence of carbonyl compounds can undergo various reactions, so it's probably best to leave this intact. What I'm noticing in this molecule is this 1,3-dicarbonyl compound. And dicarbonyl compounds can be formed quite readily from the Claisen reaction. If you didn't think about that, go ahead and pause me again and see if you can propose the disconnection now. We'll have to place our disconnection here. That's because in the Claisen reaction, the side that retains the ester is the side that enolized. Let's draw our synthons. So we have this side enolizing and acting as a nucleophile. We need this positive character here, so a way we could introduce that is by putting on a leaving group. And it makes sense to have the leaving group match this side since it's a Claisen reaction, and we usually use a base that matches the ester. So our starting reagent would be this. There's some nice symmetry going on in this molecule here. And we notice our groups, our nitrogen and oxygen groups now, are in a 1-2-3, a 1-3 relationship. Now let's cleave a bond next to our nitrogen and draw our synthons. In a previous video, we looked at something like this, and the reagent that can correspond to this can be the enone. And as long as this undergoes a conjugate addition with our enone, we'll get this pattern. So we can envision this coming from this reagent. Now, hopefully you're noticing that this side is symmetrical and we could just do this by an analogous reaction. So this would be our disconnection, and for this side, this would be our starting material again. Let's skip straight to our forward synthesis. Benzylamine, an inexpensive, commercially available compound, can react with 2 molecules of this to give this intermediate. Treatment of this now with sodium ethoxide will enolize one side, displacing the group from the other, and that will directly give us this, which we'll call target molecule 3. Wow, so we took what looked like a pretty complex molecule with 3 functional groups in it, and we were able to just make it in 2 steps. Before our final retrosynthesis, I want to just do a little bit of an aside on the Mannich reaction. This is another reaction that'll put nitrogen and oxygen in a 1-3 relationship, and I left it out of an earlier video thinking it was kind of complex because it's a multi-component reaction, but I think we're ready for it now, and then maybe we can apply it in an example. This Mannich product comes from 3 starting materials. We have an amine, a secondary amine, a non-enolizable substrate here, and then an enolizable carbonyl compound as well. This partner is often formaldehyde. Let's do a little abbreviated mechanism to understand what's going on here. So these 3 components are going to react in the presence of catalytic acid. So in this first step, we're going to have the amine react with the non-enolizable carbonyl compound, which is in the presence of acid, so this will be protonated. The amine can attack at this carbon, and we'll get this intermediate. A proton transfer will put this hydrogen onto the oxygen. Now nitrogen can kick out the water with its lone pair of electrons, forming an aminium ion. Don't forget, we still have an enolizable substrate in the mix. Under acidic conditions, this will form an enol. This enol can attack the carbon atom, pushing the electrons back onto nitrogen, giving it back its lone pair and neutralizing this positive charge. So let's show that arrow pushing. These electrons come down. These will go onto this carbon atom, and nitrogen becomes neutral again. And we get our ketone and our amine in a 1-3 relationship. Keeping this reaction in mind, see if you can come up with a synthesis of this anti-Parkinson drug. Now, if you can't apply the Mannich reaction, no worries. It's just important that you can get back to commercially available compounds. But if you can't apply the Mannich reaction, that'd be pretty cool too. Okay, well, the Mannich reaction begins with an enolizable ketone here, and we don't have that in this molecule. But we do have an alcohol with 2 groups added to it. And this just screams Grignard. So we can add Grignards of either of these pieces to a carbonyl compound and arrive at an alcohol. So it makes sense that we cleave one of these bonds if we're going to apply the Mannich reaction. So which do we want to cleave so it's the last step? Do we want to take off the cyclohexyl or the phenyl? Both of these are available as Grignard reagents. So we have cyclohexyl magnesium bromide and phenyl magnesium bromide, and we can buy both of them. Now, remember when we're enolizing, this one was a good example because it's symmetrical. So it doesn't matter which side enolizes. So if something over here is going to come from a ketone, well, we want it to only be able to enolize on one side. A phenyl ring is not enolizable. It's sp2 center right there. And so it really makes sense to cleave this bond first. And I'm going to take this straight back to the starting materials and not the synthons. This is kind of flipped over, but it is so similar to this molecule here. So we can put in our disconnections. We're actually going to have a couple when we're applying the Mannich reaction. There'll be this part coming from an enolate that corresponds to this. This carbon here comes from formaldehyde. And then this comes from our amine. This is benzophenone, formaldehyde, and piperidine, and these are all commercially available. Let's finish off with our forward synthesis. Mixing these 3 components with catalytic HCl will give us this. Adding our Grignard will make an alkoxide, and then we'll need a workup step. And let's call our anti-Parkinson's drug target molecule 4. Thanks for sticking with me till the end. And I just want to point out that you've worked on the synthesis of 4 drug molecules, you medicinal chemist, you. And so I hope you feel empowered to be able to look at important molecules and drugs and start to pick apart the bonds a little bit and think about how somebody might make them. Great work. KP here. If you learned something, give me a thumbs up on the way out, and for more chemistry, subscribe to my channel.